All right, everybody, we're going to get started here. My name is Janice Onneson, and I am the Director of Academic Initiatives at Minnesota State IT Center of Excellence, which is a part of the Minnesota State system, the MnSQL system. We are one of 8 centers of excellence across the state of Minnesota, and our area is in the information technology world. So many of you faculty or industry students are probably engaged with us through community events, through IT explorations, for trainings, for faculty trainings, for curriculum. We do quite a few things in a number of different areas. If you'd like to check out our website, it's mnstateitcoe.org, and I will put that in the chat for everybody to see. I would like if everyone could go and just make sure you're muted at this time, and that way we won't have any distractions. Our first webinar for the fall presentation here is Dan McCreary, who is a distinguished engineer for Optum. And we decided that September, with everything going on in the world, that we would have some fun with databases, with artificial intelligence. So the September 2 webinars, which happen every other week, are going to be around AI and databases. So Dan's going to start off this session with the database and AI. And in 2 weeks, we have another gentleman coming in to talk about the different devices that are out there, such as the Siri and the Alexa, and how AI is really transforming a lot of what we do as we all start working from home, going back to school, going back to our industries, and some of the new technologies that are out there. So please join us for further ones as well. So without further ado, I'm going to ask Dan to introduce himself. This call is being recorded. Your pictures will not be recorded, but your names most likely will be. So if that is an issue for somebody, please let me know, and I'll make sure that I take you off there. But we are recording this, and it will be used for further presentations as well. So with that, I'm going to hand it over to Dan, and Dan, go ahead and take it away.
Very good. Thank you so much, Janice, for all your work. Just let me introduce myself briefly. I'm a distinguished engineer at Optum Healthcare. We're a part of United Health Group. And if you haven't heard about United Health Group, we have about 330,000 employees, 32,000 technical staff. And my role is I work in the Advanced Technology Collaborative, which is a group of people that are looking at all the emerging technologies and looking at all of our business units and business challenges. And we try to help match the right technologies with the right business problems. One of the reasons I've been doing this is I'm very involved in AI education. I've been closely involved in the Coder Dojo mentoring program. And I've been also very involved in setting up something called the AI Racing League. This is the project where you take these remote control cars and you put a Raspberry Pi on top of them, and then train it to drive around the track 10 times by itself, and then build a neural network model on a GPU, transfer that model back, and if you get everything right, you press the button and your car drives around the track. And it's a really fun way to learn AI. So I'm very involved in that, and please reach out to me if there's anything I can do to help you bring AI into your curriculums in your classrooms, and we do that through a lot of the code savvy programs. So what I want to do today is just talk a little bit about a review of what we talked about last time. I realize several people may not have been in the last session we did on May 18th, so I'll review that. But what I want to do is also talk a little bit about knowledge representation and some of the incredible things that have happened just in the last month or so with this thing called GPT-3, generative pre-trained transform models. And then we're going to talk a little bit about how I think this is going to impact online learning. And the reason I want to do this is because I think a lot of the people here might be helping us build better online learning systems. And I'll talk a little bit about what we've done, some experiments on that. And then the last thing I'm going to talk about is AI skill sets. Of all the various areas of computer science, how do you get involved in AI, and what skills might be important for your portfolio as you're going out in the work field where there's a lot more AI happening. So I just want to review what we did last time. Last time we did this thought experiment where maybe you came to the Minnesota State website, and there would be a little agent in the lower right-hand corner that would pop up and say, what would you like to learn today? And this would be a chat bot. And a chat bot, then you could start to ask it questions. They said, I'd like to learn how to write a chat bot, and it would start to ask you some questions, some probing questions. It'll ask you, do you know how to program Python? Are you familiar with natural languages? Have you ever used a graph database before? And then once it asks a series of questions, it's going to go through and actually build a lesson plan for you. And a lot of the way that we study these chatbots and study about how to implement it is we have to come up with a way of storing knowledge. What does the chatbot know? How does it take these questions and match it to set some content, and then figure out what your intent of your question was, and then match it to answers, and then answer those things? So what's been happening in the last several years, since really 2012. 2012 is when Google really announced the fact that they were using graph databases behind their knowledge engines. And since then, you've seen a huge growth of interest in this one type of database called a graph database. What this is a site called DB Engines, and they have web crawlers that go out and crawl every content site that's related to technology and databases. They look at every paragraph that people are talking about. They look and they compare the words in that with their taxonomy of the different types of databases, and then they match it, and then they see what you're talking about. And you can see that the discussions, the job postings, all those things, the articles on graph databases has just skyrocketed compared to the rest. And the reason is that we've always known about graph databases, but we've never really been able to get them to run at scale. They've never really been able to span multiple data servers because they're so tightly connected, but now we have new technology to do that. So in the landscape of all technologies, database technologies, I'm the author of a book called Making Sense of NoSQL, and I break it down into the 6 basic, what we call database architectural patterns. Just like an architect designs a house and has a larger blueprint, that is the recipe for building those houses, there's really only about 6 core blueprints, and most people start out with this relational table model. Relational tables are also called a row store. We store one row of data at a time, just like a row in a spreadsheet, and we have these rules that each column has to have the same data type. And then if you want to look at relationships, you have to take 2 different tables that have different things, maybe people in one and their orders in another, and you have to join those together. And that join operation is something that wasn't designed initially. Initially, remember, these were punch cards. These punch cards got loaded into the mainframes, and we used COBOL, and COBOL's programs all did flat files. So relational really evolved out of those punch cards. So whenever you think of relational, think of flat row at a time access. And there's 5 other patterns, but what's most interesting is that graph is really taking a hold of the industry by storm, and why graph models have become so important for us to build predictive models so we can do things like predict which question comes in and how it should be matched to the right sentence. Most of the structure of language doesn't really fit into a single flat row. They have all these words, and words are connected to other words and concepts. So graph has really started to take off as its way to store knowledge. And what I wanted to do is just talk a little bit about what I do. I do this job of matching a business problem to the right which one of these patterns. And my book has this character named Sally Solution. She's a solution architect, and she has to listen carefully to what business problems you have. And she knows about all the different ways to store data. And then she knows the trade-offs. Remember, there's no one right answer. Sure, you can use almost any structure to store any problem, but what would be the easiest? What would save you the most money? What would be the most scalable? Which would be the highest availability so it wouldn't crash? And Sally's job is to know all those alternatives and then advise you to do this. Now, how does Sally do this? She has a process. And this process starts out with 2 lanes at the top. The top lane is kind of the requirements. What is it you really need to do? What are the business drivers? What are the quality attributes? High availability, flexibility. And then the second one is, which are the options that you're allowed to do? In the Midwest, we are really driven by our traditional mainframes and COBOL and Relational and SQL. So 95% of the solutions we teach in our school state is focused on what our businesses need, and that's been the Relational. But if you go to the Bay Area and you talk to people at Google and Facebook, you might know that Facebook is a network of people and their relationships, or LinkedIn, all the people that are connecting together, or Amazon that has 100 billion products in a graph, or Pinterest that has 100 billion interests and how they're related. Those companies don't use Relational because they have different challenges and different scalability, and so they're exposed to a lot of other ideas. So let's just talk about what a graph database really is. Instead of thinking of rows and columns, the graph databases think about these things called a vertex and an edge between those vertex. And just like a table has columns, each of these vertices and edges have properties, but there's one big difference. With a graph database, the relationship between objects, between any things, the nouns, is always stored as an in-memory pointer, right? There's no concept of a join. You don't have to compare a primary and foreign keys on millions of rows. It's just a pointer hop. And because it's a pointer hop, there are various queries that you do, traversal queries in graph, where you have lots of complex relationships that happen lightning fast, because pointer hops are one of the fastest operations in computer science. So as a result, there are certain transactions we do in graph databases and analytics that are much faster. Now, just to be really clear, we are not really talking about graphics and graphical interfaces, pie charts and bar graphs. We're really talking about graph as a fundamental way to store things. The atomic unit of storage is no longer a row, but it's a vertex or an edge, and each of those have properties, and they're all hooked together inside a lot of pointers in memory. As long as those pointers all fit in memory, you're usually good to go. If your graph gets bigger than memory and you have to swap out, then your query times drop dramatically. So we'll talk about those challenges. So I should also be very clear, we're actually not talking about a graphics GPU card, these graphics processing units that have been very popular in the video game industry, because those cards actually were originally designed so that when you had a 3D scene, it could rotate it and you could walk around in a 3D world. And what they were doing is they were putting that data into a matrix of values, and they were doing math on that. So it's really good at doing algebra on matrices of data. So that's really different than what we're talking about. We're talking about a database where we're optimizing to traverse those databases. So let's just do a compare and contrast now. On the left-hand side, we have a picture of our relational database, the row store, and the atomic unit is a row, and every column has to have uniform data, and the table structures are fixed in structure. All the rows have to have the same structure. And relationships are calculated every time you do a query, and they're difficult to distribute those tables over a large network of 100 different servers in your data center. A graph is on the right, and the atomic unit storage of these nodes and edges, and every node and edge has independent properties. And what's interesting is you can add new graph data to the graph almost at any time, and those relationships can evolve. The joins are all calculated when, or the relationships are calculated when you load the data. And the general rule of thumb is that if you have a core in a server, that every core can traverse about 2 million relationships per second. So if you have 16 cores, you have 32 million hops per second that a typical graph can do. can traverse. And what's important about that is we used to only have single node, and now we can distribute our graph over many different nodes in our data center. And that's how Facebook and LinkedIn and all those things scale. So the thing about this is that we're now evolving, and we're trying to marry these graphs with machine learning. So let's just talk about what machine learning really is. In the past, we used to write our code, procedural code, if then else rules. And we take these programs and they would analyze the data, and then we could say, based on these if then rules, here's the answers. And we can also explain things. The new era now is where we're actually taking a lot of this data, we're putting it into this things called machine learning. Machine learning is where we have to have a training set. We train those. Sometimes they have labels, sometimes they don't. But the bottom line is we build these neural networks, which are also the structure of a graph, but that's a separate story. And then we take the answers, the labels, and we effectively build these complicated neural networks. And if you can imagine, they're effectively a rules with tens of millions of weights in them. And with the challenge there is we don't have explainability. So now what we're trying to do is evolve to this new era where we still have machine learning, but those machines are actually going to be training the weights inside of our graph, the probability scores of how things are related. And so what's coming out of that is both knowledge and the answers, so we can explain why we're making these predictions. Now I'm going to talk a little bit about the trends in machine learning. So this was some of the analysis that have been done about how conversational chatbots have been evolving over the last just three years. And you can see back in 2018, only about 25% of people polled would actually prefer to interact with a customer service agent that was a chatbot. And what's interesting about that is just in the last couple of years, that has zoomed up to almost half of people are now actually preferring to interact with a chatbot, because the chatbots are getting better and better every year, and their knowledge is getting a little bit more general. What's also interesting about this is the amount of horsepower that we have to train these systems. And that's a 300,000-fold increase just in the last 6 years, or 8 years, because this was going back to 2012. And what was interesting is that when we started out, we were using regular processing, but then as we did it, we learned how to customize our silicon, and we customized using GPUs to train these models. So it's getting faster, and we have more and more horsepower. I should also tell you the algorithms are getting better. If you look back just a few years ago, you needed a lot more power, and now we can use smaller computers and still get the same smarts out of those systems. So let's just talk about what we do when we're building a neural network. So I'm going to show you a very simple model of a little tiny neural network. It has 3 inputs. It does a calculation of these 3 things. It adds these things together and then applies a weight, and then sends the sum of those 3 things through what's called a step function, or also called an activation function. And then that creates an output. And that's kind of the same way each neuron in our brain works. We have about 82 billion neurons in our brains, but they all have about 10,000 inputs. They add those together, they change the weights. Sometimes the weights are negative, so they're subtracting things. And then if they reach a certain threshold, they fire. They fire down the next, and they're connected to 10,000 other systems too. So this is the idea of a neural network. And what's interesting about this is by looking at how we set these up, we can count the number of parameters that we have to adjust. In this model, each input is weighted. There's a bias. And then, so we have effectively a 4-parameter model in a single neural network. Now, as we make our neural networks a little more complicated, we add a little bit more layers to this. We can see that the number of parameters we have to train in these networks goes up quite a bit. In this one, we have to count the number of inputs, the number in each layer. We multiply those together. We do some addition. We look at the things, and we can see even this small network has 32 layers. And that's a good example of a small network that you might train in a lab doing things. Now, what happens if we start to really scale this up? What happens if every time that we fed words into a neural network, we wanted to come up with weights of what's the probability of one word following another word? And that's what's really happened a lot in the last couple of years. This thing's called natural language processing, where we take an entire text of Wikipedia, we send it to these neural networks. Words are sequences of things. Each sequence is an input. When we look at a word, we look at the words around that. It's called bidirectional training. And we then come up with a probability that any word is going to be forward, before, or behind things. And this is what's been happening. This is the revolution that happened about 3 years ago, where a lot of researchers found that they could actually train their neural networks to not really understand text, but to do really interesting things with text. And there was a wonderful example that came out, and this was done by a company called OpenAI. And a couple of years ago, 2 years ago, they came up with this thing called generative text, where you give it a little prompt, a few set of words, and it looks all the words and the contents, and it tries to guess what some future words might be that might make sense. And this is if you do the searches, these are called GPT-2s. And it was really fun because you could go in and give it a prompt and it would almost write a paragraph. It was kind of made sense for the first couple sentences, but then it would kind of get a little bit more crazy. Well, what happened this summer is this company called OpenAI released this new version of their model called GPT-3. GPT stands for Generative Pre-trained Transform. They pre-train this neural network on text. And it's kind of simple. What they do is they take a sentence, they chop one word out of it, called the missing word, and they try to guess what that word would be. And if they guess correctly, they say, well, then we'll add something to the weight. If they guess it wrong, then they subtract the weight. And they just do this over and over and over. And they use very, very large data sets. These things take days and days, in fact, potentially millions of dollars of compute to calculate. They estimated GPT-3 might have cost $10 million to compute. But what's interesting about this is that it was so much bigger than the prior models. Even the models that were calculated last year were only about 1 billion. The axis on the left-hand side here is in millions. And the model that came out was about 12 million. And now they're up into the 175 billion things that they're computing. And what they're finding is every time they do this, they get a little bit more sophisticated. They span, it's not just one set of questions they can answer, but they can do a lot of other things. And so now we're starting to see this thing where it's not just narrow AI, where it just does question answering or help search, but it's more generalized AI. And we'll show you what those tasks look like. So the way these things work then is that you start out with what's called a prompt. That prompt goes into the neural network and it then tries to guess what the future things would be. There was a wonderful demonstration called Talk to Transformer. These are all called transformer models. Unfortunately, the people who set it up, they were being used so much that their fees were going up, so they turned off the free version. Now you can do it, but you have to pay some of the fees. But some of the new demos are coming out. You'll start to see those soon that they can actually do things. So you can almost give it an outline of a curriculum and it would complete a curriculum for a class for you. So those are the things about this natural language that's getting very interesting. They have ways of testing these things. So they'll give you a prompt, they'll ask you a question, and you have to figure it out what it is. And this model is amazing because some of these really hard things, which almost meant you had to know things about the real world, they are now answering these questions correctly. This prompting is something that they do, for example, if they want to have you translate things from English to French, you would have to say, here's an example of the word cheese, and it translates to fromage in French. And then once you give it some prompts, it then starts to know, oh, now I know what you're looking for, and it will start to do those things. So those are called 0 shots if you don't give it any prompts, 1 shot if you give it 1 example, and if you give it several examples, those are called few shot learning. So what does it mean to be correct in this? How do you measure correctness? And that's something that we do in statistics, and this is called an F1 measure. F1 is kind of a measure of how good is it at answering the question correctly, even if I give it some hard problems where I know some of them it's going to get wrong. Here's the solution space of what it should be right. And F1 is really kind of a mathematical relationship of something called precision, which is kind of the ratio of the green half on the left versus the total circle, and recall, which is the green half, the true positives, versus all of the relevant elements. So by doing those ratios, you can figure out how well you're doing this. And so that's how we measure the effectiveness, the quality of a lot of these AI systems. So basically what we're doing is, in the past, when we tried to take these tests and measure, did these chatbots get the questions correct on these things? What we started to see is that as we create better neural networks that get closer and closer to the size of the human brain, that their quality of measure, their F1 measures, kept going up and up and up. And we could simulate that too. We could make a predictive model. The more neurons we have in our neural network, the higher the scores it got on these tests, and we can start to see that they get better and better. And I don't want to go into the details, but these basically just show you that we have a very consistent way of testing things. And if you're going to build a chatbot, and say your chatbot should help you answer questions in your Python programming class, you need to have a list of those questions so that you can start to measure whether or not the chatbot gets them correctly. So then in June of 2010, we saw the GPT-3 paper that came out, and that was just revolutionary for a lot of people. It started to get much, much better scores. The accuracy started to go up. And the one most freaky thing, if you've heard about something called the Turing test, the Turing test is where you connect a terminal up to 2 different agents. One is a real person, the other is a chatbot, and you ask it questions. And if a person can't tell the difference, you'd say that the computer kind of passes the Turing test. Well, we're getting really close now. So this one is called a article detection, whether it's a real article or a fake article. And the way they do this is they give the GPT-3 a prompt, and they say, complete this article. And they give that same thing to a real person. And now they have human subjects trying to kind of tell, is this article, do you think it was created by a computer or a real person? And what's crazy about this is now the human tests can only detect the real ones about 52% of the time. And that is just shocking about how amazing the quality of these models have gotten. Just in the last 2 months, they have gone up so much. So, so it's changing very quickly. There's a lot of very high important things that we can do. Obviously, if you do something like Grammarly used to be kind of clunky. It's a tool to help you analyze your grammar. Now, Grammarly has been completely rewritten to use these transform models, and it is amazing. If you haven't tried Grammarly yet to look at your papers and help you with grammar, it is just an amazing thing. So a lot of these things are happening. So let's ask a little question now about what's really happening behind the scenes here. So let's take a story of the human brain. Now, remember, the human brain and a neural network are very, very different things. The human brain has immense connectivity. Every neuron in your brain has 10,000 other connectors. A lot of the graph databases I build have between 5 and 7 connections between them. So it's a very different thing. But you can see that as these networks get bigger and bigger, that they're starting to do things that are going to be important. And one of the things that I'm really interested in is, what about online learning? What if I'm an educator and I want to build a curriculum and I want to have a chat bot help my students out when I'm not available? I want to make sure I share a knowledge base with other teachers that are also teaching this, and I want those things to be easier to access. I want kids, even though they can't afford expensive tuition, that they can also take advantage of these things. So those are some of the key questions. And what I want to do now is talk a little bit about how you're going to see these things evolve in the next 10 years or so, as we have more and more chatbots come available. So if you're a fan of following Tesla and some of the things that Tesla is doing to automate their driving, you might know that there are these 6 levels, 0 through 5, because we're computer scientists, we have to start with 0. These are the levels of self-driving. Level 0 is where the car just gives you some warning if you're in your lane, maybe some automated cruise control. And then level 1 is where the driver has to have their hands on the steering wheel, but it might start to share some of those decisions, slam on the brakes if you get too close. Level 2 is where it can actually steer around a corner and accelerate and brake. Level 3 is where the driver can actually take their attention away from the screen for a while, or the windshield for a while. Level 4 is even more sophisticated, but a driver is around for safety. Level 5 is the ultimate level. Probably not see that for quite a while, but that means that you can take away the steering wheel. It doesn't matter if it's rain or snow or what conditions. There's not good marking on the pavement. There's construction, any condition that cars can do that. We're getting close to level 4 pretty fast. Level 5 is a long way off. But now what I want to do is I would like to start to think about, where would we classify this on online learning? And what I'd like you to do is I'd like you to envision a graph database that holds all the knowledge about online learning. Say you're part of a coding club. I work in Coder Dojo, so I use that example a lot. We work on understanding the relationship between the student and their content. We put all the content online. With COVID, we've had to really, really focus on getting a lot more content online so our mentors and our students can do that work autonomously. What we do is we make sure that mentors get training about the content. The mentors have a good trusting relationship with the students, so we can start to build a mental model of how these things work. We build a mental model of the coding club, of their leadership, the facilities. Do they have good hardware and software and curriculum? Are they trained? Are the students engaged? And we can then start to build what's called our predictive function. So the predictive function says we want to predict what's the probability that a student is going to achieve their learning objectives by the end of this class. That they're going to get to a certain competency level, that they can, if it's a database class, they can create and maintain and update and query those tables. And what we can do is we can start to look at training sets. We can see all the students that did achieve it. We can see all the students that didn't achieve it, and we can start to put them in a model, and you can predict what are the features that are doing that, and then we can work on making those most critical features a little better, right? So that's a predictive model of student success. Now, what I'd like you to do is, just like we took the driving levels, I'd like you to start to think about the evolution of what this online learning is, and what's going to be the role of AI in building a chatbot that can help you do this. And we're going to go through that same thing. And I'm just going to walk you through these steps. And the reason I'm doing it is because I want you to start to think about what skills you may need to develop in order to build these chatbots that are going to help other students learn. I'm going to assume that you are all interested in building agents that are going to help other people build other systems. And now we're going to go through that. So the first thing we're going to do is we're going to talk about that very initial thing about student and content and mentor. So in this stage, and this is where we're at with most online coding clubs, we have a bunch of volunteers sign up, and they have skills, mentoring skills. We have students that sign up, and they're interested in various things. We have a matching process. We match those all together, and then we have the mentors and the students do these virtual learning, and it's very initial. It's almost all manual. We put them in spreadsheets. There's no automation, things like that, and we don't store any of the results. We don't. There's a lot of concerns about privacy, so nothing is ever stored. And you can see that we're still trying to figure out how to do things better. A good example is we're starting to build what are called journey maps. Journey maps are ways that students can help to visualize the success of their learning. What are the skills they need to learn? What are the concepts they need to learn? What are the order that we're suggesting? And what are the difficulties? What are the fun parts? How do we get them engaged? Can we help students see the journey map? Can we give them an award at the end, the finish line? Can we give them a badge and a sticker for their laptop? So all those things we're trying to do, and we're trying to figure out which are the things to make our students the most successful. So then we start to go up to the next level, and we say, well, now what we have is we have these students, we have these mentors, we have these topics. What if we started to build a training model? How could we automate that? How can we automate predicting and making recommendations? Just like when you go to Netflix and it recommends a movie based on other people that are similar to you and what they liked. What if we could recommend a topic and a mentor, and whether we can match these things together? How would we use AI to map those things? How do we store that data into a graph and store all those relationships? And how do we hook those up to a neural network to help us predict if Susan has a mentor of Alice, and Alice then has familiar with those topics? We have a 80% model probability that they're going to have a great mentoring session, and they'll give us a net promoter score at the end of that session of 8 or higher, right? So we're trying to predict their ability to say that they like these things. So now we're going to go up to the next level. The next level is we get a little bit more detail in our graph models. We start to store what are called concepts. So concepts are the abstract names of things that you need to learn to master a topic. If you want to say you know arithmetic, you're going to have to know addition, subtraction, multiplication, and division. We say that arithmetic depends on those 4 topics, and we build a dependency graph and store all those things together. For every class that you take in a university setting, there might be 500 or 1,000 topics. Some of the advanced classes in graduate school might have 10,000 topics that you have to master, but you already assume that you have prerequisites on half of those. And the idea here is that whenever we're helping students learn, we realize they come into the class with an existing list of known concepts, that's in the green. They have goals, they want to learn how to write a chatbot. And we then can create a map in the middle of what are they ready to learn, because those things depend on other concepts. So this is called the zone of proximal learning. And so we're going to start to add those to our map, and we're going to maps and our graphs, and we're then going to suggest content to learn those concepts. So content is different. Content is a physical book or a Wikipedia page or any of these other things. And then we recommend the content to help them learn those concepts. So the 2 names sound very similar, but one is an abstract thing, lives in a dependency graph. The other is a document that you're going to give the student. And there's a lot of many-to-many relationships. A single book may cover many topics. A single chapter in a book may cover many topics, and they depend on other topics. So what we recommend as content really depends on where the students are, what concepts they've mastered, and how do we find out that. A great mentor is somebody who knows what you know, has a really good picture of mental image of you, and they'll recommend the right concepts, the right Python program. They'll know your background. They'll know the problems that you might have with that. If you don't, they'll give you the right background, and they'll help you get up to your learning objectives. So now what we're going to be doing is we're going to start to use intelligent agents to recommend which of those things, to predict the right things. So imagine this graph that's getting more and more complicated, and students will come in and they'll state their goals, and the agents might ask them questions, the probing questions, the background, and they'll start to recommend content and and education and learners. So now I'm going to ask, so what is the role of natural language processing? What are all these things that we've learned about BERT? Now, what we found is that these intelligent agents can actually answer questions, and they can understand the context of a class. And if we gather the right data, if we log all the right data in our training, they are really going to be smart at telling you what to look at. So say you have 10,000 students that have all taken Intro to Python, and you are really good at keeping detailed websites of exactly which page in the online curriculum they've gone to, which slides they've seen, which exercises they tried, how long it's taken them to do each exercise. And then they get to a certain stage and they say, oh, I have this problem. I cannot figure out lab number 7. I can't figure it out. And the agent should be able to say, well, we've analyzed all these other students and we predict that if you put the debugger on and look at the index value on line 25, you'll be able to figure out the problem. So they'll start to suggest things for you. Now we'll always have mentors in the background, just like a driver will still have to take care of the cars for a while. But what we're going to start to see is these optimized AI agents are going to start to take over. And the whole thing about this is, do we have enough training data to help train our agents so that they can become smarter, that we can gather this information? Now, I'm not saying this is easy. And the reason is that your learning history is really a very important piece of confidential information, right? You don't usually publish what your grades are in all of these classes. Those are considered privates. And we'll never be able to build intelligent agents unless we have access to that data. So the question is, who will gather that data? Where will they put it? Who will have access to it? What agents will have access rights? And there's lots of legal and privacy issues here, but you can see that these agents can be more successful the more data they have. There are projects in China right now where they have a little bit more control over some of the state agencies, where they are gathering billions of data points and building graphs that recommend these things today. So there are a lot of people are breaking ground, and there's commercial companies that are trying to do this too. All right, so that's the next level of movement. And then there's going to be level 6, which is the autonomous agent learning, where you're going to sit down and you're going to just have the agent do more and more, and maybe the mentor is in the distance in the background, and you'll only engage with the teacher or the mentor when you want some career advice, or you want very high-level strategies of learning, or you maybe want to connect with other experts in the field. But what we're going to start to see is more and more of these intelligent agents are going to start to take these things over. Now, I don't want to scare the teachers or anything like that, but I do want to emphasize that the opportunity of students to take a lot of these resources and to learn these things is going to go up, and we hope that access will be more universal. I want to take the Wikipedia example, right? 20 years ago, if somebody said, you know, there's going to be an online knowledge place and people are just going to donate their knowledge for free, and it's going to be all tied together, and it's going to be where the students all go to learn things, I would have said that's crazy. And I think the same thing is going to start to happen here. We've got to figure out how we go from content to concepts in graphs, and to figure out how those graphs and how those predictive models are going to be happening. So a lot of challenges. One of the things I'm finding is that just getting teachers to put reusable content online is a challenge. Many of you have heard about GitHub, where we store our source code. There's a new version of that has come out called GitHub Pages, where we're effectively maintaining websites for all of our projects. There's a markup standard, which is much easier to learn than HTML, called just Markdown, where you have very simple things. And we found that teachers and instructors and mentors really prefer just maintaining all their content in this Markdown standard. But then we have to transform it into web pages. So that's a make docs, the transform process. And then we want to have a lot of richness in our materials. We want to be able to put in code fragments and notes and annotations and all that stuff. And there's a wonderful set of libraries that came out of Google called Material Web Components. So we use make docs combined with material, and then we're starting to get all this ability for people to put their content together on the Coder Dojo pages so that all of our tutorial clubs around the world can all share and remix and use that content together. But we're not storing any student information, right? It's all kind of forbidden. We don't do any of that. We just are trying to facilitate, and we're trying to guess what are the aspects of that are. So some other organization is going to have to figure out how to do that. Privacy, student record privacy is really important. And the idea of portability between computer systems. If you go from one school to the next, do you want to have them input all of your known concepts again, over and over again? Or can we make assumptions about those things? And then there's a lot of ideas about rating. Remember when I talk about recommendation? One of the reasons that Netflix is good at recommending content, or Amazon is good at rating products, is that every time you buy a product, you can give it a 5-star rating if you think it's great, or a 1-star if you think it didn't work. So how do you rate content? How do you rate mentors? Who's going to rate those mentors? Where are you going to store that thing? Maybe a mentor is really good at teaching cell phone development, but not very good at teaching Python, right? So how do you do all that weighting things? So there's a lot of challenges here, a lot of them things, but I can tell you that the capabilities of these computers today, I'm working on a project right now where we're building custom hardware to accelerate the matching of patients with their care paths. And in 2 years, we're expecting a 1,000-fold increase in performance, or conversely, the costs of doing these graph recommendations are going to drop by a factor of 1,000. I'm working with some of the most advanced executives at Intel to design a new set of processors that are going to make that very, very fast. So what does it mean? It's going to mean it's going to be very inexpensive if we can solve the security and the privacy issues. And some organizations are going to take that on and figure out how to secure and hold that data. So I'm hoping this is going to be a positive impact for society. Any technology has pros and cons. People can use things in nefarious ways, and we have to figure out ways to detect that and find that. But we're hoping that this educational content will be free, and that the recommendation engines will be low cost, that learning will be democratized, everybody will have access. And what's important about this is I'm expecting the people that are hopefully listening will be helping us build those future systems. So what are the skills you're going to need? Data literacy. Data literacy is probably the one thing that employers are asking for the most. They want students to come to them that understand about data, how to analyze large sets of data, not just what's in an Excel spreadsheet, but what goes beyond that. Data science, probability, statistics, linear algebra, very important. That's probably linear algebra has probably taken over calculus as the most important skill in AI and machine learning, because all of this data we put into these big matrices and we use them to solve problems. All of the students that I'm working with and the interns and our programs are all using Python and Jupyter notebooks, which is the modern learning stack, PyTorch and TensorFlow. I hope that you study data structures and graph, and this one thing called a labeled property graph is by becoming the really big way to do that. Web and user experience have to make sure that you know how to build these user experience things because they're really essential. And the user experience things is changing quite a bit. Every 18 months it's changing. I think I've been through 6 different types of user interface tools in the last 10 years. And it's probably going to change again, especially when you have mobile phones that these things want to support too. So with that, I think that's all the material I wanted to cover. With that, I'm going to open it up for questions.
Wonderful, Dan. This is Janice. That's great overview, as well as some very specific things from educators and industry that we can do and move forward on, and especially with the students that are listening in here, kind of giving you a career path around what AI and graph databases can do for you. So if anybody has a question, now would be the time to ask Dan about either what's going on here, or if you have a question in general. about AI or graph databases, please unmute yourself and go for it.
I think people are shy today.
Well, this is Mark Swanson. Back at the beginning of the presentation, you had an example, a slide that showed a relational database, which we're probably all very familiar with, and comparing that to the edges and nodes and so on in the graph database. Could you give an example of what exactly is in these nodes and how that would compare to a relational table?
Sure. Each node in a graph, also called a vertex, has a list of properties, just like you have columns in a table. And those properties have data types, strings, dates, integers, and things like that. And then the interesting thing is edges also have the same list of properties. The types of data structures you have as a property also are a little bit more varied than a traditional relational database, where you often have just string and date and things, but then you have a thing called blob. Within graphs, they usually have things like lists and sets are also a data type that's associated with an attribute of a vertex. But if you think of something that has a bunch of properties, and those properties have a variable name and its value, that's really what it is. And the key thing is that there's no rigid structure in a graph. You could have any number of them in a lot of graph databases. Every vertex can have different types of structure. So we often call it open world. Anybody should be able to add any facts to any vertex in a graph at any time.
So then, similar to looking at like JSON data or something like that, you'd still have to have a program that understands what all of those properties of each vertex are and knows what to do with all of those.
Yes, that's right. So for example, JSON is really kind of a hierarchy of values, more of a document store. And so if you wanted to load a JSON file into a graph, there'll be a loader program, and that will look at the different key values in the tree and then place them at the right spot of the graph. JSON is an ideal way to send data into your browser. It's a single document that contains that tree of data. Most modern databases have ways to ingest JSON and map them into the right things using what's called a mapper tool. A mapper tool often gives you a tree on one side and the graph, and you literally draw the lines between the two, and you'll do those maps.
Excellent. I got a couple questions in chat, and then I'll get to Tony has a question. Chad Eka says, what are some other projects you've worked on that impact healthcare outcomes?
Yeah, great question. I think one of the biggest things that I've been doing is semantic search. So search is very important for our customers when they're asking questions about their healthcare plans. And they often use words that are different than our clinicians use. So I help build search agents, and a lot of chatbots also do search. So I'm trying to make it easier for people to get their questions answered by our call center agents. Making the job easier for our call centers. United Healthcare has about 50,000 people every day that answer questions about your benefit plans. So a lot of my work is using Graph to integrate all that data together. In the past, that data used to take a long time to integrate, and now we can integrate that much faster. Customer agents used to log into 13 different systems to answer questions, and now they just bring up one big graph display in a timeline view, and those things are used from there. So a lot of that also is moving into the clinical setting, where we take care guidelines. We use NLP to process those guidelines, we convert them into decision trees so we execute rules in our clinical systems. Those also are very, very heavily dependent on graph databases in clinical. One of the key things about clinical data is it's got lots and lots and lots of relationships. Many companies have tried to store patient records in rows and tables, and they usually get to about 1 million patients, and their databases will fall over and just stop performing. In a graph database, we just don't have those joint penalties, so it's ideally for storing clinical data. I think you'll also find that educational data, the relationship between students and a course, every course, of course, has learning objectives. Those objectives have content. You have a book have chapters and paragraphs and concepts and all those things. There's a massive amount of knowledge in education, and we should be able to start to track and log all those things and help build better predictive models to help our students overcome learning problems.
Wonderful. One more, and I do have a comment. Yes, this video will be available to all the attendees. We'll have it on our website very shortly here, as well as I'll send it out after this recording, so you'll have this to be able to share or to review again. We have another question from Stacy Schaefer. How important is it to know linear algebra to the skills of Python or data science?
Great question. And I would say it's knowing Python in our world is kind of the basic language. We used to teach Java, and we used to teach other languages, but Python is just really, especially in data science, just taken over. Almost all the new things out of Google and Facebook, everything is now just Python libraries that are published in things. So Python and Jupyter Notebooks are, I'd say, like the foundation of the house. But then learning linear algebra is kind of like the first floor, right? You have to understand how we represent this data in matrices and how they're used to train things. So I hope everybody really focuses on their linear algebra classes. Calculus is a little bit important, but not nearly as important as linear algebra. And then we build on those things. So I hope that helps.
Yeah, excellent. Tony, why don't you unmute yourself, ask your question, and that will wrap up the session here.
I am actually a student in Tony's class.
Oh, okay.
Okay.
I was wondering, on the issue of privacy and security, I'm not sure if this would be the most ethical solution, but what if you were able to implement a solution where you gave an artificial intelligence enough cognitive functionality, or maybe trained it to have enough cognitive functionality to be able to identify threats within its own organization to the system, like to the information that it is supposed to protect?
Right. Right. So there are intelligent agents that run on our networks every day that are looking for threats. And they're not just external threats where people are trying to attack our websites looking for vulnerabilities, but they're also internal threats, right? So all big companies that have a lot of data to protect, we build a model for each employee, and that determines what kinds of authentication you need. So if I have access to 10 databases that have all the student records, I'll have to have two-factor authentication to get in. Whereas if you are just an administrator and all you look at is your calendar, maybe one factor is enough. So we dynamically calculate on the fly internal and external threats, and we use graph technologies to do a lot of that.
Okay, that kind of answers the question. But then I was wondering so this might not be the most ethical way to implement this, but what if the artificial intelligence was capable of predicting an employee's behavior through a psychological profile that it builds up based on its interactions with an employee?
Yeah, good question. Let's just say that we're not going there. It's possible. I think if you work for some of the very, very secretive defense agencies, psychological profiling is something that you go through when you're obviously when they interview you. But there are also methods of monitoring that on an ongoing basis. I do know that companies read email, and they can look for psychological behaviors in that email and send alerts to human capital or human resources people. So yeah, I'm glad you started that out with the ethical question, right? Because this is really important. AI is bringing up so many ethical questions. Every day I'm confronted with ethical questions about whether we can use a certain data set to train certain things when the contract says this way, and if we interpret the contract this way, we could use it, and if we interpret it another way, we couldn't use that data to train a model, right? And so, yeah, ethics is everywhere. I hope everybody does have a chance to spend some time in each class. I don't think you should just take one class in ethics. I think every instructor should spend about 5% of their curriculum talking about the ethical issues that are uncovered in a lot of these classes. So it's really important we all start to think about this and think of not just about the short term, but the long-term societal impact of both doing things and not doing things. So great question.
Wonderful. And with that, we're going to wrap today's event up. I did receive a couple of emails from folks who also have questions, so I'll make sure that I send those off to Dan. If anybody has other questions that come up along the way here, you think back on the presentation, we are in contact with Dan. Dan is more than happy. I'm sure I'll speak with
Absolutely.
you.
Yep.
But more than happy to answer questions, especially the ones, you know, from the students who are looking at what does a career in this area look like. We have some wonderful partners with Minnesota State IT Center of Excellence. So I really encourage everybody to reach out to us if you need a connection with Dan or any of our other speakers that we have. And I really appreciate you taking the time to be part of this webinar series. Again, look at our IT Connect, our events calendar on our website, and we will have more of these to come. Dan, thank you very much again. As usual, you've done an outstanding job at creating some real intriguing and opportunity views within the data area, and I appreciate that very much.
Thanks for doing this, Janice. I really appreciate it.
You're very welcome. And with that, I will say goodbye, and thank you all for attending.
Thanks. Bye, everybody.